So thank you very much for coming. This is going to be a talk about mazes and the pythonic way to some pythonic implementation of the mazes, which means graphs, basically. So I try to not to be too much scholastic. So if there are any questions during the talk, please feel free. No problem to interrupt. Okay, so first of all, a bit of clarification about the terminology. Mazes means graph, and maze traversals related problems are the topic of this talk. Mazes are basically the everyday data structures for instance, RPG addicted gamers, just like me, or just like I was. So another title for this talk could be the Hitchhiker's Guide for Getting Out from Dungeons in Dungeons and Dragons. About the adventures or the algorithmic adventures, algorithms are the most important and durable part of computer science because they can be studied in a language and in a machine-independent way. I will try to introduce a bit what I mean. But in this talk, we try to do that from a very pythonic point of view. And by the way, this is not supposed to be an algorithmic class, of course. Unfortunately, we will not have the time to be exhaustive on this topic because it's very huge. I try to just provide hints about some specific references you may look at the end of this talk. And again, we are interested here in the pythonic way to do the implementation. Very few basics about the algorithm analysis. We need basically a technique to compare the efficiency of the different algorithms we want to implement. In this case, we're going to implement algorithms about graphs and traversals, so algorithms that needs to analyze the structure of the graph and see what does it mean in a few minutes. There is, in the literature, the so-called RAM model of computation. And in all the cases, we are interested in the worst-case scenario. Okay? So we want to analyze how much an algorithm is efficient considering the worst-case scenario. The RAM model of computation considers simple operations to be one-time step. So basically, the cost of these operations is constant or is considered constant. So in this case, if we have arithmetic operations or if or call to other methods, these in this model computes just like a constant cost. Loops and functions are not considered simple operations, of course, and each memory access takes exactly one time step. Thus, in conclusion, we have as much memory as we need in this model, so the memory issues is not considered. It's, of course, is a very simplistic approximation. And the RAM model takes no notice of whether an item is in cache or disk. In the literature, there are these three notations. This is the most famous, I guess, the big O notation, which refers to the worst case complexity. The theta here is the average case, and the omega is the best case complexity. The big O notation, which is originally the big omicron, indeed, means that we're interested in defining a function. This is an asymptotic complexity, of course. So we're interested in trying to define a function, f of n, with respect to another function, which is g of n, and we want to check if there exists some constant c such that f of n is always less than c times g of n for large enough numbers. In other words, this means that here is the function here times n squared. This is the n here. Sorry. Okay. In this case, we may say that the time t here belongs to big O of n squared. Okay, because for at some point the complexity is dominated by the n squared function here. So an algorithm that belongs to these set of functions means that in the worst case, the overall complexity will be equal to big O of n squared, where n is the size of the input. Okay, so if you have an algorithm that needs to operate on lists, for instance, n is the size of this list, and this algorithm takes a time to complete which is proportional to the square of the size of the list. Is that clear? Asymptotically talking, of course. The different time complexity could define a sort of hierarchy. So we start by the constant time here, and then we have a logarithmic, a linear, a log linear, a quadratic, cubic, polynomial, exponential, factorial, so on. Okay, this is just the most famous ones. This means that if you have an algorithm that is linear with respect to the size of the input, okay, and you have another algorithm which is logarithmic with respect to the size of the input, this means that the second one is more efficient than the previous one. Okay? So this is very important, and these becomes important to consider when n is a big number, of course. So if you have to sort, for instance, a set of numbers, let's say 1 billion numbers, okay, and you have a sorting algorithm which takes the square of n, and you have another one which is log linear, so n log n, you have to properly choose which one to use. Because in the first case, the time required to complete is proportional to the square of 1 billion. In the other case, the time necessary to complete is proportional to 1 billion times log of 1 billion, which is a very different number. Okay? So this is why computational complexity is important. So let's talk about graphs very briefly. Graphs are one of the unifying themes in computer science, and I'm quite sure that you've worked with graphs in most of your time, and many, many times, and probably more than you expected. Graphs are one of the unifying themes, as I said, because they are great data structures and a powerful mental model. In fact, you may work with graphs explicitly because you know that you have to deal with graphs, or maybe you may think about your problem in terms of graphs representation. For instance, graphs represent transportation networks, social networks. It's a very hot topic in these days. Dependency networks, for instance, the dependency of a software package with respect to other pieces of code. And, okay, so, sorry. Graph in the literature comes in different flavors, so they have different expressivity, and you may choose which representation best suits your problem. In a nutshell, we have a graph which is a couple of V and E. V stands for the set of vertices, and E is a set of edges. Let me please ask a question. Is there here any of you that doesn't know what a graph is, or how these is it represented generally? Okay. I expected you. You're the worst one. Anyway, so when I said that a graph here is as a couple of two sets, so vertices and edges. It's quite clear for anyone. Okay. So vertices with an edge between them are adjacent, and the edge is then incident to both. We have G prime, which is V prime and E prime, is said to be a subgraph of G, where V prime is a subset of V, and E prime is a set constituted in this way. Sorry for this. This is the LaTeX that's not working. We have all the edges, which are in E prime. There are a subset of edges of E, which are incident in at least one of the two nodes interested in the edges belonging to V prime. Okay. And finally, we define a path in a subgraph, which is a subgraph where the edges connect the nodes in sequence. And a cycle is like a path, except with the exception that the last edge links the last node to the first. Okay? I mentioned the flavors of graphs. We may have undirected versus directed graph here. Okay, so in this case you have direction. You don't have directions on the edges. Here you have the directions. So you have a direction to follow. I mean, if you have an edge here, you may follow this edge traversing this maze, this graph. You may traverse from this node to this node in both directions because you have no constraint on the edge to follow. In this other case, you're constrained to follow this connection only in this direction. That's basically the difference. Okay. Moreover, you may have weights on the edges. So usually these weights correspond to cost. So for instance, you have a graph here with different weights, and you want to reach this node. You want to start from this node and reach this one. And for instance, you're interested in know which is the path that connects this node to this one that leads from this to this at the minimum cost. Okay. There is a simple versus a non-simple graph. Here, the simplicity means that there is no cycle here. These are the loops, or cycles. These are loops. The loops are the cycles from a node to itself, basically. And as I said, cyclic versus acyclic. I'm quite sure that you know that trees, for instance, are connected acyclic and directed graphs, or we may have DAG, which is directed acyclic graphs, and you may have an algorithm which is called topological sorting on these graphs. But it's out of the scope for this talk. And finally, you may have labels on the vertices or the edges of the graph. And another very interesting representation of graphs is for sparse graphs. This is particularly interesting, especially if you consider their representation in data structures, so in computational data structures. Sparse graph is a graph where only a small fraction of vertices have edges, and in the case of dense graphs, basically there is an edge connecting each edge to any other. Or another flavor, for instance, as I said before, explicit versus implicit. In this case, you explicitly know that this is a graph. In this case, no. So finally, let's talk about graph representation. So let's dig into the code. The very simple way to represent graphs, and just to remind you what a graph is, we need to represent vertices and edges. Okay, so we have sort of vertices, and we need to represent how these vertices are connected to each other. So the very first and simple representation is the adjacency lists. It's one of the most intuitive ways of implementing graphs, and for each node we need to access this list or set or iterable in Python of its neighbors. So for instance, let's consider this graph. we have nodes labeled from A to H in this, and we want to represent this one. A very straightforward implementation for this structure. We may assume that we have numbered the nodes. So for instance, A is the number 0, B is the number 1, till H, which is number 7, n minus 1, because we're in Python 0 indexed, blah, blah. Okay? And, okay, so here is the set of our nodes. And N is the structure of adjacency, so the neighborhood, to represent the neighborhood. It's a list where each element is the set of neighbors. Okay? So the name N has been used since in graph theory, because N of V is the neighborhood of V, these vertices. And similarly, we want to implement this function here. So N of V is the neighborhood of node V in Python here. Okay, so this is the representation of a neighborhood as a list of sets. Can you read this from the back? Too tiny. Okay, thank you. So if we want to know the length of the neighborhood of a node, we may simply apply the len of n of f. In this case, is 3. F is here, and n of f, sorry, that's a mistake here, of course. At least there is, see, okay. They're not the same graph here, sorry. Okay. We may check if if vertices here is in a neighborhood. So this is the new neighborhood membership test for this structure. And okay, so this, so far so good. Another implementation for this could be to replace the sets here with a list, and we see the difference in cost, for instance. Again, we may check the length of the neighborhood of a node, which is called the degree of a node here. And we may check if a neighborhood, the neighborhood membership, again, with the same syntax. So basically, the two structures are the same from a syntactical point of view. So the two operations here are quite the same. Okay, but the difference is in time. For instance, the neighborhood memberships takes theta of n of v in this case. Right? So basically, it's linear to the size of the neighborhood in both the implementation. But on average, for sets, it's 0.1 because the implementation of sets in Python. Okay, so this is one of the difference. Of course, this implementation can be very problematic if the graph is dense. For instance, we could leverage on sorted adjacency lists and bisect. Bisect is functions already implemented in Python, in case you don't know it. And in that case, if we basically what's said here is that if we need to check if a node becomes to a neighborhood of another node, we need to look for the neighborhood and check if that node belongs to that set or list. Okay, so it's basically a sort of searching algorithm. Not a sort of, it's a searching algorithm. Okay, and in general, searching algorithm takes a time which is linear to the size of the structure you need to look on. Okay, and but if that structure is sorted, you may apply a bisect search proportional to the logarithmic of the size. Okay, so basically a number which is less than the linearity of the linearity search. So we may implement we may sort this list and then look for the memberships using the bisect algorithm. Another trick, for instance, we may, instead of using lists or sets, we may use dictionaries. Okay? In this case, this implementation, I think it's quite straightforward and allows for a more expressivity. Because in case you have weights on this, for instance, you may use this implementation to have the node and the weight of the edges. This means that here we have an edge connecting the node A from the node B, and the weight of these edges too. Clear? Okay. Moreover, this is a way to implement sparse weighted graphs, for instance. It's very simple. And again, we may apply the same functions applied before for the degree or the neighborhood membership. With the same syntax, pretty easy. With a bit the temperature. Another, moreover, we may also check for the weight of edges in this case, because in this case, n of A is the dictionary and n of A of B is the weight. Basically, n of A is a dictionary, n of A of B is the key in this dictionary, and we got the weight here in this implementation. So it's very straightforward to use. Of course, we may have a more flexible approach, and this approach follows the indications about the Python patterns to implement graphs. You may check these link in the official documentation of the Python programming language. Basically, this is a very straightforward way to implement graphs. Here you have a dictionary where the key is the label associated to the edge, and to each label a list of the labels is associated, which is the list of edges connected to these graphs, to this node, sorry. Okay. If we want to try a different implementation, we may try a dictionary with adjacency sets, for instance. But in this case, we need to drop the weights info. It's a very still implementation, but it depends on the rest of the code, of course. In this case, so here we have a dictionary with adjacency sets. So here we have a key, which is B, is the label associated to the node. B, we check if is in the neighborhood of A, okay? And we may check for the length of the neighborhood of F in this case, so basically the degree of the node. So at least we drop the weights info about the syntax for these two basic operations on the graph is the same. Another implementation, another structure to represent the connections between nodes in a graph is the adjacency matrix. It's another very common way to represent graphs. Basically, we list all the neighbors for each node, and we store the value indicating the presence or the absence of the edge in the graph. So basically, it's matrices where true means there is a connection, false, there's no connection. This is a sort of example. Here, again, we have the nodes. We may have this matrix, which is basically represented here as a list of lists. And where there is 1, it means that there is a connection. When there's 0, means there's no connection between the nodes. So if we want to check for the membership of the neighborhood, sorry, okay, connected. Want to check for the neighborhood membership, this is applied in constant time. Okay, so it's not linear anymore because we just need to access the information stored in the matrix. And if we need to count, to check the degree of a node, we need to sum over the values corresponding to the list of the of the node, in this case the F node. Okay, so in this case the degree of a node is no more a length function, it's a sum of 0 and 1s over the list corresponding to the node. But please consider that this is constant always, because it's just a lookup on this table. Okay. Of course, even if we gain improvement on the neighborhood membership, we of course lose in terms of space required to implement the structure, because in this particular structure we are just implementing the entire information embedded in the graph. Some properties of the adjacency matrix. Of course, the diagonal is equal to zeros in case there is no loop, which means that each node is not connected to itself, of course. And in case of undirected graph, which means that you may traverse the edge between two nodes in both directions, regardless of the, as I said, direction of the edge, the adjacency matrix is symmetric, which means that if there is an edge connecting A to B, of course, there is 1 in the location of B connecting A. Okay? So basically, the adjacency matrix is symmetric. Another very important property for adjacency matrix is that if we want to extend this representation to weighted graphs, it's quite easy, because instead of storing 0 and 1s in the locations of the matrix, we may store the values corresponding to the weights of each edge. So let's take a look. In this case, we may assign to this variable the infinite, and the infinite here means there is no connection, because we want to allow 0 as a weight. Okay, so if we have infinite here, this means that there is no connection between that two nodes. In the other locations, we have numbers here, and these correspond to the weights of the edges between the nodes. So in this case, the neighborhood membership code turns in this way. So inf is the float of inf, and W of A and B less than infinite is the neighborhood membership. So this means that if it is inf, this means that there's no connection. Otherwise, there's a value, and that value is the weight, but we just want to know if there is an edge or not. Okay? And this is, for instance, another test. Want to check if C and E are connected. In this case, C and E here is an infinite value. Okay, so this test fails, and in fact it's false. This means that C and E are not connected to any edge, by any edge. And in the code for degree is a bit more complicated, but it's quite straightforward, I guess. So we need to sum the ones. So basically, we iterate for each. Basically the degree of a node is the number of nodes connected to that one. Okay. So since we have weights, we need to count each weight as 1. So basically, here the code is what it does. Basically, substitute each weight with a 1 in case that weight is not infinite. Okay, so the sum of the degree is the sum of every value different from infinite minus 1, and the minus 1 is because here we have the zeros on the main diagonal. If you want a reference for a very good book on efficient graph representation, this is very, I know, quite academic, but it's very interesting to take a look. Okay. There are 2 methods for representing graph, and this is quite at this point, you know that there are two methods, and these two methods are those you may have heard in some class during your study at the university. Okay, but there's a classical misconception about this. General graph representations are always presented in terms of adjacency lists or adjacency matrices. Of course, it is faster to work with adjacency matrices, but they use more space, as I said, than adjacency lists. So we'll choose one or the other depending on which recursion is more important to you, and depending on the fact that you're working with, for instance, a dense graph or a sparse graph. There are many interesting ways to represent graphs: edge lists, for instance, or incidence matrix. Okay, so in case you're interested in representing different information, you may take a look at different sort of data structures specifically devoted for this kind of implementation. Moreover, there are specialized representations of graph types, for instance, trees or interval graphs. Trees, in case you don't know, are a specialized version of graphs. Are graphs where you have no direction, you have one node, which is a special one, which is called the root node, and you don't have cycles in this graph. Okay? If you have to deal with trees, you have other data structures. Of course, you may represent and implement a tree by using an adjacency list or adjacency matrix, but of course, that's not the most efficient way to do it. Okay? So the rule of thumb for this, the takeaway notice is decide on the asymptotic overall complexity and decide which type of graph you need to deal with and choose the best representation for it. Okay, so we finally arrived at the second part of this talk, traversing mazes. So just to have at glance, what does it mean? Here you have a map, okay? So you have walls, you have walls, you have blocks in your corridors, and a partial traversal is a very typical situation in which you end up playing at role-playing games. Think of the rooms as nodes and doors as edges, for instance. The traversal tree is definitely by tracks. And the fringe, so the traversal queue, consists of the neighborhood rooms. The remaining darknet rooms haven't been discovered yet. Okay? So are the nodes that you may know they exist, but you don't know. This is a description taken from the literature of the traversing mazes, which says that basically the completely traversable passages of a labyrinth twice for any initial point simply follow the routes posed by Tremo, making each entry or exit from an intersection. Basically, this means that when possible, avoid passing an intersection you have already visited, of course, and avoid taking passages you have already traversed. So just take a look at this. Sorry. Again. Okay. This approach wouldn't then tell you to start walking in a direction and then backtrack whenever you come to that end. Backtrack means try to a step ahead, step by step return on the path you followed. And in case of an intersection, in case you didn't take that before, try that intersection. So basically avoid cycles. So this is the very simple implementation of the arbitrary walk. So here in input we have a G, which is the graph, and S, which is the starting node. Here we have P and Q, okay, which are respectively a dictionary and a set in Python. P of S is none, of course, and Q is the implementation of fringe. So basically the nodes we need to traverse. Okay. while the queue is not empty, we take randomly, indeed not randomly, we pop out, pick one arbitrarily, but the implementation of pop in Python is quite straightforward. So we would pick a node in the edge. We iterate over the neighborhood between the nodes already visited here, P, and S, and P of S, which is the list of nodes we're tracking over the walk. And then if there is no there are nodes already not discovered, add that node to the fringe and go ahead. And basically finally return P. P is the path, of course. The traversal tree. So the walk function will traverse a single connected component, and P is the predecessor string. In this case, if we want to, with this function, the walk function, if we want to check all the connected components of G, you have a list of here of connected component. Basically, you iterate over G, you walk G, considering each node of G, and you have C in output, and basically you add these connected components. So basically the connected components in a graph are all the different parts of a graph that are connected, basically composed by nodes connected to each other. Okay? So are subgraphs in which you may always find a path connecting a node to another one. Okay? The time complexity of these algorithms is proportional to the size of the edges plus the size of the vertices. In case we want to visit the different nodes of a graph, there is a very well-known algorithm which is called the depth first traversal, and the quite straightforward implementation we learned at the algorithmic class at the university is the recursive one. So basically here we need to check at each step if we add the current node to the fringe, and then we iterate over the neighborhood of that node. If that node is not in the fringe, we call again the function recursively on the node of the neighborhood of the S node, and we go deeper and deeper. So basically, it's quite simple to imagine these algorithms working on a tree, for instance. So basically, if you start from a root node, and then you go deeper and deeper, going following the different child you find on the path until you get on a leaf, which is basically a node which has no adjacency, no neighborhood, and then you step back recursively. Okay, so you step back. Thank you. You step back in the parent node, and then go again recursively deep in the structure. Okay, it's quite clear, this example. It's very simple for trees. Okay, but we know that recursion in Python is not a... So basically, we may re-implement these algorithms in an iterative way. And this implementation is very simple. Basically, we implement by queue, which is a list. The stack, of course, we would perform recursively. So it's very easy. In walk implementation, we use a set, so we would risk having the same nodes scheduled for more than one visit. And in DFS, DFS stands for depth first search, we use LIFO queues, which means last in, first out, so basically a stack. So in this case, every node is scheduled for visit only once. We have, of course, we may implement a general traversal algorithm. And for instance, here, according to how you implement, this is very interesting. You may, for instance, decide which kind of traversal you want to implement, depending on the type of queue you use. For instance, in case you use a stack, so basically the add operation here is a list.append. Okay, in this case, if you call traverse here without specifying the queue type, so basically the implementation of a fringe is yes, the implementation of the fringe here is a set. You do the arbitrary walk. If you pass these with the stack, so basically as class we extends the list and has the add method, because the add in the list there no exist in Python, so it's just an alias for list.append. You implemented the first traversal with just the same traversal algorithm. Okay, just changing the type of queue you're using for traversal. And moreover, here you may use the yield statement instead of the return for a lazy iterations. It's very interesting because in case your graph is very big, the depth first traversal becomes crucial. The performance of these graphs becomes crucial. In case we have infinite mazes, I want to skip a bit because I'm running out of time. So I want to just go to the end of this and want to find another very interesting thing is about the shortest path. So as I said previously in the example, if you're interested in check if two nodes are connected, plus you want to find the conduct connections in the minimum number of intersections. So the minimum number of edges followed, for instance, or the edges with the minimum weights or the minimum cost. There are many algorithms about it. The first attempt is the iterative deepening depth first search. So the basic idea of this algorithm is to yield the list all the nodes that have been discovered and apply a DFS when the depth limit is D. So you put a bound on the limit. But another interesting algorithm here, the breadth first search is quite famous as the algorithm. Let me skip this. It's very similar to another one. I mean 2 minutes. Yeah, thank you. So I want just to show you, okay, this algorithm about the shortest path. There are many algorithms in the literature, depending on you want to calculate the shortest path starting from a specific node, or calculate all the possible shortest paths, regardless which is the starting point you choose in your graph. Let me just show you the last slide of this series. I will, of course, share all the materials online, so you may take a look at the slides I have the time to talk to you about. Dijkstra algorithm, Python is Dijkstra algorithm is very interesting, but I need to skip it. Okay, that's what I was looking for. The shortest path all pairs. Shortest path all pairs means you want to the Dijkstra algorithm is give me a graph and as input, give me a node from which I need to start, and then find the shortest path connecting that input node to all other possible nodes. So at the end of that algorithm, I know that starting from the S starting node, I know which are the paths connecting each other nodes starting from S. This other problem is I want to, regardless of the starting point, I want to know if I pick randomly a node in the graph, I want to know exactly all the paths connecting from that node I picked randomly, the path at the shortest path, so the path at the minimum cost. In literature, there is an algorithm which is basically solved with a programming technique which is called dynamic programming, which may be, for instance, summarized by don't repeat yourself. And this means that you don't have to calculate the minimum path of pairs of nodes in case you already have visited it. And these could be implemented in Python with a technique, or in general, with a technique which is called the memoization. So basically cache the values you have already seen, okay, and which corresponds to the sub-problems, so the problems you have already solved. And in case you find, again, the same problem, take the value from the cache instead of computing that same problem again, okay? And this is the memoization technique. And these could be a very interesting implementation of the memoization decorator in Python. So in Python, we have the wraps from functool. Here we implement these memo, which is going to be a decorator. And we get an input a function. We have a cache here, which is basically a dictionary. And thanks to the wraps decorator, in case we have the args of the function, and if the args is not in cache, we actually compute the function on these arguments, and then we store the returning value in cache. Otherwise, we return the values taken from cache. And we may use these decorator to implement these literature algorithm, which is called flight workshop algorithm, which is the literature algorithm to calculate the shortest path for all pairs of graph, which is basically, so, anyway, we can decompose the problem as it follows. So this is the definition of the problem according to flight workshop. I just wanted to, okay. So, in Python, we have the flight workshop here. So this is the implementation, okay? And basically, we here implement the graph, the graph as an adjacency matrix, -5, wow. And in this structure, we store the flight workshop definition of minimum path here. And this is the classical implementation found on literature book. But if we want to do it recursively but memoized, thanks to the memo decorator we defined, we may have here the same implementation, but the function we modify here is the function to calculate the minimum. So basically, it's very straightforward because we apply this function for each of the nodes here, iterating over the graph. References here. This book is very interesting, and from which most of the code has been borrowed. And the algorithm design manual, just for deeper introduction of these topics from a more technical and theoretical point of view, not Pythonic. The first one is more interesting because it tries to introduce the main topics of algorithmic class using the Python code. So if you have questions, please feel free, and thank you very much for your patience.
Okay, so actually we're running on a very, very, very tight schedule. So we have just 5 minutes. So let's say 2 questions. So who has any question that he's really curious to share? Or she? Absolutely.
Hi. I found myself using NetworkX module when working with graphs. So I would like to ask you if there is any case in which personal implementations works better than using the NetworkX implementation.
Maybe, oh, sorry. Maybe this is something I should have said before starting this talk, because of course, all the code presented in these slides are not code, of course, because NetworkX is a very brilliant library for graph, for dealing with graph, and it has many of these algorithms already implemented and in a very efficient way, and sometimes even farther, may I say, because they're implemented to support, for instance, all the computation over multiple pores. This talk is basically motivated from the fact that in case you're dealing with your algorithm class and you want to implement what you see as a sort of pseudocode on the book, you may implement it in Python in a very straightforward way, very similar to the pseudocode, and you may have different implementation and different implementations of different complexity in terms of complexity, but of course my suggestion is go ahead with NetworkX.
Maybe a very, very last question. You have
another things, just a bit. Another very important thing to say in case you have to deal with sparse graphs, you want to take a look at the sparse matrices support in the SciPy package. That's another very interesting hint I would like to share.
First, sorry for my English. Second, this is a bit lateral question and not about the main topics of your talk.
No problem.
When I'm very fascinated about networks and graphs, but in some situations when I try to visualize them, I suffer of football syndrome. You forgot to talk about graphical visualization, but there are some way to reduce the pain about to look a wonderful, colorful, great football on my screen.
I think that the answering this question requires a bit more than the time I have. And very shortly, I may say that there are many, many libraries for graph visualizations. NetworkX has some very, at least at the best of my knowledge, it has very basic support for graphic visualization, but has some. So you may start looking at the NetworkX in case you already you didn't do it already. But then there are some libraries, especially in JavaScript, I guess, that allows you to visualize and dive into the details of the graphs, especially for very large networks. Because if you, for instance, have to deal with very social network, they're very big usually. So, but we may talk later for details if you know.
So I'm very sorry, but we have to ask you to please go outside. And maybe if you want to have some discussions with Valerio, you can continue outside because we have to prepare for the keynote. So if
you need to join the rooms,
yes,
that's fine.
Exactly.
Thank you very much.
Thank you.
Sorry.